today's video, we're going to dig into the Functools module. Functools is an interesting assortment of utilities that altered functions or methods in some way. We'll divide this video into four main sections: caching, parcels and reduce, wrapping, and finally dispatches and total ordering. My name is Jake, and this is a Python standard library. We'll start today with what I think is the most useful part of Functools, caching. But you can also check the description for timestamps to each section. Now, Functools offers three main cache decorators. That's cache, cached property, and LRU cache. Now, I've seen a decent amount of confusion between the three of these and when you would use them, so that's what we're going to talk about today. And the first thing we're going to look at is the LRU cache decorator. LRU standing for least recently used. Least recently used meaning that once we hit the max size that we specify, as soon as something else gets added to the cache, what would be the 129th entry to the cache, whatever's the most stale item in the cache is removed to make room for the new item. So we'll only get up to 128 items in the cache. LRU cache also adds some support for strict type checking for cached items. Another important note here is that the only things that can be cached are things that can be hashable. It's the same rule for keys to dictionaries. You can check if something is hashable by running hash on it. And here we see the hash of the string has this hash value. So let's see this in action. So we'll clear that, go back to our file, and let's define a new function using our LRU cache. And since I wanted to demonstrate the functionality where it pushes cached entries out, we're going to set a max size equal to 3. And our cache function is simply just going to be add 5, which is going to take some number. It's going to print that it's adding 5 to that number, and it's going to return that number plus 5. Easy enough. So if we reload this file in IPython, we now have that function available. And if we were to add 5 to, say, 15, we see adding 5 to 15, and it gives us 20. We call it again, it doesn't print anything out. However, we keep adding entries in, we get 12, go back to 15, doesn't need to recalculate it, and then 27 recalculates that, gives us 32. Now if we were to do one more in here we'll do 30, it should have pushed something out. And what it'll push out is the stalest item, which since we called 15 after 12, it looks like 12 should have been pushed out. So if we run it against 12 again, we should see it print out the text, adding 5 to 12. And adding that back in, pushed out 15. So if we run 15, we see it recalculates. There's some other cool things you can see from this cache method, is that the decorator also adds some information to the function itself. So if we look here under the attributes available, we see cache clear, cache info, and cache parameters. First, let's look at the cache info. This tells us how many times it returned a cached value, how many times it had to calculate a value, the defined max size, and the current size. Since we're at 3, we're at our limit. And if we look up in the output, we should see our 2 hits here. And those 2 hits in order are here at output 2 and here at output 4. Everything else is part of those 6 misses. Now, aside from cache info, we have cache parameters, which aside from the IPython warning, just gives us the explicit and implicit arguments that were passed into our LRU cache. Here you see we specified max size of 3, and the default for typed is equal to false. Now, more useful than that is cache clear. So if you want to invalidate the entire cache, you can clear it. And after being cleared, we see it currently has 0 hits, 0 misses, current size is 0. So if we recall add 5 on 15 again, it recalculates things. Not too bad. So if at any point you decide you need to programmatically clear a cache, you have that option available to you just by running cache clear on it. And just like that, those are the basics of how all of these cache methods are going to work in Python. So what is the difference between LRU cache and this other cache method? What it all comes down to the behavior that we see in LRU cache. If we look at the docstring for LRU cache, we see something really important here. If max size is set to none, the LRU features are disabled and the cache can grow without bound. What this means is it no longer has to do any checking to see the size of the cache and whether it needs to pop things out. It'll grow as much as your system has memory for, which is something you may need to keep in mind if you're going to be caching a lot. Now, the authors of Python decided that instead of having people specify max size is equal to none all the time, they would create an alias to this functionality here with the LRU part disabled by simply letting you delete that parameter and delete the LRU part and give you this cache decorator here, which is literally an alias to LRU cache max size equals none. So if people ask you what the difference between the two is, now you know the answer. So let's really see this caching in action. We'll give ourselves some more room, and to demonstrate the caching, we'll go the classic Fibonacci route with a really poorly implemented Fibonacci function. And what I mean by this function being poor is that while it does work, it's pretty inefficient and relies heavily on recursion. But it's in this recursion that our cache really shines. So we'll also make a cached version of this, literally calling it cached fib. And the way we're going to test this is with just a simple benchmark called benchfib. We'll just have it calculate the Fibonacci number up to 38 because I think that will more than demonstrate our point. And there we go. We have a simple benchfib function, which is going to get the start time. It's going to run our Fibonacci function up to the goal. It's going to print out our time taken without caching and then with caching. So if we load this up again and run benchfib, you see it's taking some time to calculate it. And look at that. Without caching, we're up to 6.816 seconds, but with caching, we're all the way down to 0.00003 seconds. Because each time that I had to do the recursive calculation, it was just looking up the value that it already calculated before. So when we got really high up in the numbers, like around 35 or so, instead of recalculating 34 and 33, each of those are requiring recursive calculations among themselves, all the way back down to 1, it just returned the previous result, giving us one heck of a speed up. So just like that, we see the power of caching. As a matter of fact, with this function, even with a small cache, we'll see a pretty sizable speed up. So if we reload that and run benchfib again, you see that even with a max size of just 2, we're substantially faster. If we bump that back up to 3 and run it again, we see that with a max size of 3, we're already back to the same speed that we saw with an unbound cache size. And we also saved a bit more memory there too. Okay, now let's look at our cached property. For cached property, we're going to do something a bit special because this has to be done within a class. So we'll create a new class called metar. And these are basically weather observations. So I'll write out the class and bring you back when I'm done. Okay, we're back and our metar class has been written out. What this is going to take is known as an ICAO code, which are international codes for airports. Every recognized airport has them, and they're a great way to look up weather information at the airports because the vast majority of airports around the world also have weather sensors there because they're extremely important for aviation. So what this class does is it has a number of properties associated with it. It has this data property, which is going to download the latest observation for the airport and then return the JSON data. And then some other properties so we can look at things like the raw observation, the temperature, dew point, and wind at the time. Now, right now I haven't added any caching into this because I want you to see what it looks like before we add caching. So we'll load up the file and we'll create a new instance of our metar class, passing in KRDU as our airport code. Now, when we run krdu.data, which is our property, it'll pull all the information down, of course saying that it's getting the METAR for krdu. And here we see all the information about the site and the observations at the specific time. If we look at some of our properties here, like raw, we see, again, getting the METAR for krdu. It's having to download that data again and process it through the JSON loader before it gives it back to us, which are then accessing the items from the dictionary here. This is especially bad for something like wind speed, because we need to put two different fields together. They're using self.data twice. So if you look at krdu.wind, it downloads the data twice. Obviously, this isn't ideal, not only because it takes time, but if this were some type of production application, we'd be hitting the API a lot. And this particular API does have rate limiting. So eventually they'd start rate limiting our requests. But the way we get around this is really easy. Since we already imported cache property from Functools, we can just change this property into a hashed property. And that's it. This time, instead of krdu, we'll use rjaa. And if we look at rjaa.raw, we see that it's getting the METAR for rjaa and gives us our observation. Now, if we look at wind, of course, this is super basic, so I didn't add any error checking in here. We'll just strip out the type conversion, save it, and try again. We get rjaa again, full raw, and then let's look at that wind one more time. So for some reason showing none there, which we could look into the data and see why that is. But the important thing is that we're not seeing we're getting the METAR for rjaa again, because we changed data into a cached property. And that's all it takes to implement a cached property. Pretty easy, right? So for the amount of effort that it takes to add caching from Functools, you really get a lot out of it. Okay, let's talk about partials and reduce. Partials are definitely more commonly seen around Python code than reduce is, but they're both neat in their own way. So where a partial is used is to build in an argument into an existing function in a way that you don't have to pass it again. So we'll use URL open again and return back to a function that we saw in a different way in a previous video. And that's going to be our get site status function. So the way we would typically use this is we'd call get site status, passing in the URL of some website, say google.com. And we'd have to do the same thing for any other website that we want. You're getting the picture. And anytime that we wanted to check the status of Google, we'd do the same thing. Run get site status, pass in google.com, and go from there. But what partial lets us do is to make things a bit more simple moving forward. Say we wanted a new function called Google status, dedicated solely to getting the status of Google. Well, all we'd have to do is call partial. We're going to be passing get site status into partial, and the argument that we're going to bake into it as a partial method is google.com, which is going to create a new function for us called Google status. And we can do the same thing for Facebook here. Again, we're going to call partial, and instead of calling get site status with that, we'll just change the signature here. Call partial get site status with facebook.com. We can repeat that a few more times to have specific site statuses. So now we're starting to see the use of partial here, baking in arguments to give us dedicated functions. So if we load this up, we should not only have our normal get site status function, we should also have our dedicated ones, like Google status, which we just need to call as is, and we get 200. Same thing for Facebook status, call as is, 200. Red Hat status, sure enough, 200. And finally, X, which apparently this time didn't like being called X. So let's check the site status for its former name, twitter.com. And we get a 200. Looks like they haven't fully made the change as of the time of this recording. And with that, you get the idea of how partials work. So similar to partials are partial methods. Because if we look at a class and class methods, create a new class here called VM Manager, which is going to have a single function in here called toggle power, which is going to take an argument of self and toState, which will then just do this. Toggling the VM on or off, depending on the state that you pass in. Now, if you were to try to use the normal partial on this method here, it really wouldn't work out too well, because the first argument that goes in here is self, and that's the instance variable. The argument that we'd actually want to bake into a partial would be toState, so we can't really use the normal partial here. Instead, if we wanted to do partial versions of this, we need to use partial method, and that will look like this. Partial method, we're going to make a partial method out of toggle power, and what we're going to bake into this is on, and we can store this as a new method on this class called power on. Copy that one more time, change on to off, and you guessed it, we now have two new methods here that use toggle power but are simply called power on and power off. If we load the file, create a new instance of VM manager, and say vm.poweron, we call that, we see we're powering on the VM. And same thing for power off. We're powering off the VM. Of course, at any time, we could always call toggle power and set it explicitly to off or on, however we want. But with the partial methods here, it gives us a way to make little help methods by baking in arguments to another method. Not too bad, right? Okay, let's change things up a little bit and look at reduce. Now, I'll admit, this one's a little bit weird, and the uses of this are definitely much less common than we could see partials in Python. But I do think it's important to understand the behavior here, because when you see reduce, it's typically not immediately clear exactly what's going on. So let's demonstrate this. Create a new function called multiply, which is simply just going to take two numbers. And you guessed it, it's going to multiply them together. So far, pretty simple. But let's play around with this. I don't think we really need to test the behavior of multiply, so we'll skip to just using reduce with it. Now, the arguments to reduce seem a bit intimidating, but at its very base level, it's going to take in a function and some iterable. So let's try it out with multiply. That's going to be our function, and our iterable is going to be a range from 1 to 5. We'll start simple. And we see we get 24. But what's going on here? Well, let's alter multiply a little bit and make it a little bit noisier. Then try that reduce one more time. And now we're starting to see a little bit clearer what's happening here. First, we get multiplying num1 by num2. So it's going through our range. And remember that evaluating this range will give us the numbers 1 through 4. So the first thing we see is it's multiplying 1 by 2. So it's going through our iterable. The next time through, it's giving us 2 and 3. So we may think that it's moving forward within our range, moving to the next pairing. But if we look at this final statement here, we see 6 and 4. Well, that's not what we thought, right? What's really happening here is it's taking the output of the previous run and feeding that into the next run as the first value. So multiplies 1 and 2 together, which gives us the value 2. It feeds 2 in and pulls the next value from our range here, which is 3. Multiplies 2 by 3 to get 6. Then feeds 6 in to the first number within multiply, and then passes in our last value of 4. Let's try this again, this time moving from 5 to 9. And here we see 5 times 6 is 30, so it feeds 30 in as the first argument the next time around, multiplies that by 7, gives us 210, which it feeds into the first argument again, and so on until it moves all the way through. So this definitely can be a bit confusing, right? But there are some uses for this. One use, if it didn't already exist in the Python standard library, would be to construct a factorial function. And we can actually combine this with partial. So we'll make a partial out of reduce, and we'll pass in the multiply function here, which will create a new factorial function. And with that factorial function, we can pass in, say, a range of 1 through 20, and that computes the factorial all the way up to this ridiculously huge number, which, of course, This already exists within the math module, so we can check our value there. Max here going up to 19, we see we get the same value. If you have any interesting uses of reduce, be sure to let me know, because again, I've not seen it used too much, but I think there's some interesting cases that could be done. Now for wraps and update wrapper, these are almost exclusively going to be used when you're working with decorators. I'm not really going to cover decorators in this video, but if you're unsure what they are or want to brush up on them, there will be a link in the top right now. But for this example, let's consider what we see on the screen here. We have this decorator, print time, which is going to decorate some function. And what's going to decorate is this perfect function here. So if we load this file, we can take a look at perfect function. Then it's going to have some attributes to it, like under doc, saying this is a perfect doc string. And it also has its own name, which of course is perfect function. But if we were to apply this print time decorator manually, overriding perfect function, we now have a new decorated perfect function. However, this one isn't as perfect. If we look at the doc string, it's missing. And even more concerning, if we look at the name, it's now wrapper. That's because this decorator print time is actually replacing perfect function with this wrapper function here. So let's clear that, reload the file, and this time let's actually store the decorated perfect function as a new function called decorated. So this again is going to call print time, pass in perfect function, and now we have decorated, which as before has a under name attribute of wrapper. What we can do here is we can use update wrapper to update decorated with perfect function. And what this does, if we take a look at decorated now, look at under name, we see perfect function. Additionally, if we look under the doc string, we see this is a perfect doc string. So what this does is it copies over important attributes from the function that you're wrapping over to the function that is wrapping it. Now what specifically is being copied over? Well, we can look at the help text for update wrapper, and we see that has a few arguments to it. The first being, again, the wrapper function. In this example, we literally had a wrapper function, the function that is being wrapped, this one being perfect function, and under here we see an argument called assigned. And these are the default attributes that are being copied over from the wrapped function over to the wrapper function. In here you see things like name and doc, as well as some other important defaults like module, file name, and annotations. There's one additional thing in here that's also kind of interesting, which is an updated field, which will copy over the contents of the dict from the original function. Now, this isn't used nearly as much, but it does have some uses, and we can demonstrate this pretty easily. So if we look at perfect function right now, and specifically its dict, it doesn't really have anything to it. But an interesting thing about functions in Python is that they are still objects. So you can assign random attributes to them. So now under perfect function, it has a something attribute, which has the value test. And this will now show up in its dict. Now decorated currently doesn't have that. If we try to access something on decorated, we're going to get an attribute error. But we can call update wrapper again. And now when we try to access something, we get test, because it copied over the entire contents of perfect functions dictionary. Okay, so now we see how update wrapper works. But how do we use this in our code? Well, one thing we could do here is we could call update wrapper, pass in the wrapper function, as well as the function that's being decorated. And this is perfectly valid. In fact, if we were to test this out ourselves, doing another assignment of decorated, manually applying that print time decorator to perfect function, we'll see decorated.name isn't wrapper anymore, it's now perfect function. So we definitely could do that if we really wanted to. However, there's a cleaner way to do this. And what we'll do is we'll move update wrapper to the top. And instead of calling it update wrapper, we'll call it wraps. And this will be a decorator. And since it's a decorator that's decorating this wrapper function, we no longer explicitly need to pass in wrapper here. So we'll just delete that argument. And now we have the wraps decorator passing in the function that we're decorating, which is perfect function. So if we apply this decorator, we now have our solution. And finally, loading the file one last time. We have perfect function. We look at its doc string. This is exactly what we expected. This is a perfect doc string. If we look at its name, it says perfect function. So as far as we can tell, nothing has really changed here. But let's go ahead and run perfect function. And here we see different behavior to perfect function. We see, of course, it printed out that it finished being perfect. And then we see that it also printed that perfect function took 1.00 seconds to execute. Well, of course it did, because it's perfect. And that's the beauty of wraps here, is that it keeps all that metadata that someone would expect from a decorated function in place instead of overriding it when you're replacing it with a wrapper function. Now for the last things we'll cover in this video, single dispatch and total ordering. These are some interesting helpers that you may not come across often, but when you need them, their functionality is definitely handy. So single dispatch, that sounds weird. But what single dispatch allows you to do is to handle different types of arguments differently. If you're familiar with some other languages that have operator overloading, this is somewhat equivalent to that. However, it only considers the type of the first argument. So let's try this out. We're going to use single dispatch as a decorator, and it's going to decorate, in this example, a single function, which will be handle error. Now, handle error is going to take in some type of error, and we can either provide some type of default behavior here, or what we can do is we can raise a not implemented error as our default behavior. Now, just like this doesn't seem pretty useful. But it's what we're going to do next is where you're going to really start to see some of the magic associated with single dispatch. Because decorating handle error here actually gives us a new decorator. And that decorator provides another decorator called register. And in here we can register specific behaviors given a specific type. So if we wanted to handle a type error, we can create a new function that'll do just that. Now, one common convention you'll see when dealing with single dispatches is not to actually name these additional registered functions, is to just give them a single underscore, because the name isn't really going to matter in this regard. It's all going to be done under handle error. Again, this will take in an error and will handle it. So now our handle error function, if it receives a type error, it'll implement this behavior. We can copy this over a couple more times to handle things like value error, zero division, or any other type of error that we want. So let's take a look at this. We defined our single dispatch up here, which is called handle error. We then registered specific behaviors given the type of error that handle error receives. So when it sees a type error, it's going to execute this function. And when it receives a zero division error, it's going to execute this function. And you can define as many of these as you need. Now, while this is definitely a much more common practice in other languages, single dispatch definitely still has its use in Python. If you have examples where you've used it or seen it before, tell us about it in the comments. Now, based on our imports, see we've already used single dispatch. Like we saw before with caching, we also have a method version of this. So single dispatch method. Because remember, with single dispatches, it only checks the type of the first argument. So if I were to create a new class called mynum and write out a quick implementation for it, it currently just has a single method, addIt, which right now doesn't do anything. But for mynum's addIt, what I want it to do is to be able to handle 3 different things being added to our number. The first will be a normal integer, the second will be a string, and then the last one is going to be a list. And each of these needs to behave differently. Of course, in our addIt function, we can always just do if checks to check the type and then implement those different behaviors, but that's not really exciting, and that's not the example we're going to go with today. Because of course we want to use our single dispatch method. And again, we'll raise a not implemented error for our normal case. And next we'll register our implementation methods. We're going to register for an integer. Then we'll do another for a string, which is going to do a simple type conversion on another. And then finally, we'll do one for list, which is going to iterate for every item in another. And we'll call self.addIt on that item. That way our list doesn't just have to contain integers, it could also contain strings or even other lists containing integers or strings. Okay, Let's save that, and then add another section down here to our scriptified testing section. It's going to test out that functionality. And there we go. We create an instance of mynum called thenum, passing in an integer 5. Then we're going to add in another integer 13, a string 7, and then a list containing an integer 1, a string 2, and an integer 3. So let's save that, clear it, give ourselves a bit more room, and run it. And here we see under testing single dispatch, we have 5, which is our original number, 18, the result of adding 13 to it, then 18 plus 7 is 25, and then adding in our final 3 numbers brings us all the way up to 31. Pretty good. So while of course this could have been done with if-else statements handling each of the different cases here, using single dispatch and registering specific methods is also pretty nice. And this is definitely useful when you're not doing something as simple as adding things together, or even adding things together with different type conversions. If you have much more complex behavior that needs to happen depending on the type of the value that's passed in, single dispatches definitely become much more useful. Okay, and then on to our last section here, which is going to be total ordering. Now this is another thing that I think, just like single dispatch, isn't really named in a way that it's obvious what it does. But basically what total ordering does is it helps to fill in missing comparison methods for your class, meaning you really only need to define gender equals and one other method. In order to demonstrate total ordering, I've created a class here called badInt. And this is an integer class whose comparison is based solely on the length of the integer, not the value of the integer. So let's load this in IPython and take a look at it. Okay, so if we create a new badInt called 5, passing in the integer 5 to it, we can start to check its equality statements. So if we check to see if 5 is equal to 7, we see true. Because again, remember, it's checking just by size. And we've also defined the less than operator. So we can check to see if 5 is less than 15, which also is true. If we were to reverse that and check to see if 5 is greater than 15, we get a type error saying that greater than is not supported between instances of badInt and int. Okay, well that's not ideal, but there's an easy fix, because since we've already defined gender equal and less than, all we have to do now is decorate badInt with total ordering, save it, reload IPython, recreate badInt, and then redo that check to see if 5 is greater than 15, and now we see false. It's because since we've implemented these two, Python will use them as the basis for the rest of the equalities. So then greater than equal works, less than equal works, etc. And we get that all for free just by decorating the class with total ordering. And that wraps up this video. And this stop on the Python Standard Library tour. If you learned something new, please consider subscribing to the channel and sharing this video with your friends. If you have any questions or comments, please consider leaving them in the comments section below. And as always, thanks for watching.